Welcome back to week 11. In week 11, we were discussing the topic of heteroscedasticity, and we did discuss what is meant by heteroscedasticity, and we also saw the reasons for heteroscedasticity. So in very short, we discussed that heteroscedasticity refers to the case when the ordinary least square assumption of constant variance for error terms get violated, and the reasons for that are the misspecification of the model, the incorrect transformation of the data, or the uses of cross-sectional data, because the cross-sectional data by itself have a problem of heteroscedasticity due to the observation of different diverse observation in the data. Or we also discuss the case of the use of sophisticated techniques for the data collection. So the today lecture is focused on the consequences of heteroscedasticity, that what happens if heteroscedasticity is in the data, what is the consequences on the ordinary least square estimators. Then we are going to use some real world data, and we're going to see that how we can check for the applications of heteroscedasticity. We are also going to check and apply some tests which can help us to detect heteroscedasticity in our data. We will be focused on graphical method, BP test, and white test. However, there are a few more tests. We will briefly discuss these tests as well. So let me start with the consequences of heteroscedasticity. So the next logical question would be that, okay, we know what is the problem of heteroscedasticity, what causes heteroscedasticity. The next logical question is, why should we be concerned about heteroscedasticity? What are the consequences of heteroscedasticity? So let me take you to the consequences of heteroscedasticity. If heteroscedasticity exists, there are several consequences that we should be concerned about. So let me start with the first one. We say that when there is heteroscedasticity in our data and we apply OLS method, we estimate OLS, we obviously can get OLS estimator. The software do provide that, but there is a problem. What is the problem? The problem is we still get unbiased and consistent estimator, but they are less efficient, making statistical inferences less reliable. The estimated t value, f value are not to be reliable. Now, we says that the estimators are unbiased. First thing is, what is unbiased? So let me revise that. By unbiased, we mean that the expected value, let's say we talk about the first coefficient or the second coefficient, that's the, let's say we say about the beta 2. So the expected value of beta 2 is equal to the population value. So when a parameter is unbiased, let's say we talk about beta 2, so the expected value of beta 2, the estimated value, the expected value on average, your estimator is equal to the population parameter. So that's the unbiasedness. And then we say it's consistent, and then but it's less efficient. So the efficiency get affected. And when efficiency get affected, we cannot trust the t value and the f value, or in another word, the parameters values are okay, but we can't trust its standard error, and obviously the standard error lead to calculation of t statistics and f statistics, and we cannot trust these values. So if I put it in more concrete words, we say that the estimator are not best. Now, what is less efficient or what is not best? This means that when we say the word blue, best linear unbiased estimator, so unbiased got clear when we say that this property of expected value of the estimated value being equal to the population parameter value, so that leads to unbiasedness. OLS estimator are linear by definition, so that's hold true as well. And then we say best. Best refers to when you have a class of linear parameters being estimated by different methods. OLS gives you the estimator with the lowest variance. OLS estimators gives you the parameters with lowest variance or standard error. But when there is a problem of heteroscedasticity, the variance is no more the lowest. So that's a very serious concern. So the estimator we estimate in the presence of heteroscedasticity, they are not efficient or they are not best. So for that reason we say that OLS estimator during the because of the heteroscedasticity are simply linear unbiased estimator, not best linear unbiased estimator. So they are no more blue. This is a very important concern. So because of that we say that we can't trust the values of T statistics and F statistics. So let me put it in the entire picture. We say when there is a heteroscedasticity in our data and we run OLS estimators, what happens? The estimator we get, they are still unbiased, they are consistent, but they are less efficient. And by less efficient we mean their variance are no more lowest, or they are no more the best linear unbiased estimators. And since their standard error are not reliable, so we can't because the standard error is not minimum, so we can't trust the value of T statistic or F statistics. So in principle, when we estimate OLS model through in presence of heteroscedasticity, we can trust the values of the coefficients, but we can't trust the values of its standard errors. So then when there is heteroscedasticity, we can still get blue estimators, but we have to use a different method which we call weighted least square method instead of the ordinary least square method. We're going to see that later on when we will discuss the problem, the remedial measure for heteroscedasticity, and we're going to talk about weighted least square method. At this stage, I can just tell you that weighted least square method is one way of applying or should be applied when there is a problem of heteroscedasticity. So three things being discussed till now. The first, heteroscedasticity. What is heteroscedasticity? Then why heteroscedasticity? Then the consequences of heteroscedasticity. Now moving ahead in the topic of heteroscedasticity, so we can think of detection of heteroscedasticity. Obviously, once we know the problem, once we know why it happens, once we know that what are the consequences of it, the next obvious step is that we think about how can we know that our data has a problem of heteroscedasticity. We know that what is heteroscedasticity. We know that because of that our estimator are not blue. We know what causes these things, but apparently how we going to detect heteroscedasticity. So I'm going to do the theory part first, and then I'm going to discuss the theory and using the real data through Eviews and checking for heteroscedasticity. So let me start with the theory, the overview. So this is an overview slide. To start with, you should note this with yourself and be prepared to answer this always. Cross-sectional data had mostly problem of heteroscedasticity, so that's by default. Now, if you have the cross-sectional data, you should always be suspected that your data have a problem of heteroscedasticity. On the other hand, if you have a time series data, you should be more concerned about autocorrelation. We're going to see that autocorrelation at a later stage next week. For time being, we are focused on heteroscedasticity. So cross-sectional data, there should be a bell in your mind that there may be possibly heteroscedasticity in our data. So heteroscedasticity can be checked via number of ways. The first way is a graphical method. So that's kind of not a perfect measure. It's just a kind of ad hoc way of looking into and getting the first symptom of having heteroscedasticity in your data. The second one is a British pageant test, and we're going to see that BP test, that how this is a proper statistical test. We're going to see that how it works. Then we have White test for heteroscedasticity. Then we have some other tests. There are a long list of tests: Park test, Glacier test, Spearman ring correlation test, GQ test, and a few more as well. So there are a number of tests of heteroscedasticity. So before moving to next slide, I would like to mention that in order to check for heteroscedasticity, you can use just one test out of these four. Graphical method excluded. So you got three categories of tests. You just pick one test and use it for heteroscedasticity. It's up to you. In general, all these tests do agree on presence or absence of heteroscedasticity. So just pick one, BP test or White test or some other test being mentioned here, or the software you are using. For example, we are using Eviews. So Eviews do provide most of these tests, but if you are using some other software in future, you may just be limited to use one test of all these tests, or maybe multiple. So it's up to you. I would just advise you use one test. In case you have to check heteroscedasticity, just use one test and report that you use this test, and this is the this test is showing that if there is heteroscedasticity in the data. Okay, so now what we are going to do now, before going further, I didn't tell you how we can check heteroscedasticity through graphical method, or through BP test, or to the White test, or to the other tests. I didn't tell you, and it's for the reason because I want to tell the theory and I want to apply it instantly. So that's the reason I hold the detail till the application part. So now what I'm going to do is I'm going to take the data, real world data, and I'm going to use the heteroscedasticity test and all these methods one by one mentioned in the previous slide. I'm going to tell about each method, about its theory, and then I'm going to apply that on Eviews, and then going to discuss its output, then going to the new method, telling you about that method, and then telling you about the output of that. So that's how we're going to proceed further. So let me start. This is a small task. Again, I would say after this slide, you should pause your presentation, take the data, download the data, and run it on Eviews. And if you do that along with this video, it will help you to learn it, and you will be able to apply these tests very easily then. So let me start with practical task of heteroscedasticity using Eviews. I put here 10 minutes, but it shouldn't take more than 2 minutes with you. So first of all, you need data, obviously. So I put the data for which we are going to use for heteroscedasticity in your LMS. You can download it from there. Now, let me say something about the data. The data which is in your textbook, which we are following for our course, that data is on some US case study. I didn't like that study, so I just ignored that data. I took some other data, so from some other book. So the data which I took is on a number of variables, and I have listed here these variables. So the first variable is mileage, MPG, mileage, or average miles per gallon. So it's a transportation data, and this is based on different kind of vehicles and their data, that how much a particular vehicle or car give mileage per gallon of fuel. So the other variables include horsepower, HP, the engine horsepower, the SP, the top speed miles per hour, and then WT, the vehicle weight in hundreds of pounds. So these are the variables which we are going to use, and the model which we are which we are going to estimate is including the mileage per gallon being the dependent variable, and then it's being regressed on the top speed, miles per hour, the horsepower of the engine, and the vehicle weight, the three variables. So we can add more variables to it, but for this particular case we can just stick to this three variables. So I limit your data to these three variables as well. So what we are going to do, first of all, we are going to estimate this model, and then obviously we need to interpret the results, and then we should think about the presence of heteroscedasticity in our data, and obviously we have to justify your answer. So my advice would be, stop the presentation here, pause it, go to your LMS, download the data, run this model, and then think about the nature of the data, that this data contain the, let's say if I talk about the context of Pakistan, so we took the data on Toyota and on Toyota different versions of let's say we focus on cars, so we took cars, different kind of cars Corolla produced, and then we think about the different kind of car versions produced by Honda, Suzuki, and then some other brands which are not having the local assembling, and instead of imported cars, so we can add more to it, some European brands, and we collect these data, these four variables associated with all these companies I mentioned, and we took their data. So some cars may having a horsepower engine of let's say, well, we don't use here horsepower, but so you can think of in terms of the process we use like 300 cc or 1500 cc or 1800 cc or even higher, and you can think of the top speeds, or we use it per hours, kilometer per hour instead of miles per hour, and then you can think of the weight as well, we use it in kg rather than kilogram, rather than pounds. So you can think of having such kind of data. Now think about it. Will there be some possibility of heteroscedasticity in this kind of data? So think about it. Pause your presentation, estimate this model, and think about this. Have your answer ready, and then we see what I have for you. So okay, so now I will switch to my Eviews, and I'm going to run this model in Eviews. So let me switch to Eviews. This is my Eviews file, and this is the data I have. And if you look into the model, I have four variables, three independent variable and one dependent variable. The dependent variable is mile per gallon. Then I have the three independent variable, horsepower, then the top speed, and then the weight of the vehicle. So I'm going to regress mileage per hour, mileage per gallon, and I'm going to regress it on horsepower, top speed, and weight. I think that was the order. So I'm going to open these as a group. So this is the variable, I open them as a group, then I go to view, sorry, proceed, make equation, and I am going to take the constant to the start, and I'm going to run the model. So this is the results I got. Dependent variable, mileage per gallon, then the constant term, coefficient 189.9597, SP coefficient minus 1.27, HP coefficient 0.390, WT coefficient, weight coefficient minus 1.90, their standard error, their T statistic value, their probability values, R square value, the probability value, the F statistic value of, and the probability value of the F statistic. So this is the results. Now let me take you to the results part. So once you run the data, once you run the model, once you got the results, so this was the model which we run, and this is the results. So now some obvious interpretation of these results, when we look into the result, this is the horsepower and this coefficient is positive. So what would you expect? This is the result. So now as we expect, mileage per gallon is positively related with horsepower and negatively related with speed and weight. So when speed and weight increases, you would expect a kind of a negative relation, which is very obvious. And now our main focus was on the heteroscedasticity part. So what do you expect? Will there be any heteroscedasticity in the data? And if yes, why? Well, a very obvious question is that this is a cross-sectional data. Why it's a cross-sectional data? Because you just went in the market, or you just went and you collected the data in a particular given period of time during a year. You ask the people, or you collect the data from the firms and you recorded it. So it's just by nature a cross-sectional data, and we already said that the cross-sectional data would have a problem of heteroscedasticity. But if you dig it down deeper, you see that you are combining different kind of cars, a car having a lot of weight, a car having lesser weight, a car being manufactured by one firm, by another firm, using more or less perhaps same kind of assembling technique, but obviously using different kind of components and differentiating their products. So at the end of the day, you are combining the data with a quite diverse kind of units or observation in each of your data. So that's by itself, or by its nature, having diversity in the data. So obviously you should suspect your data with the problem of heteroscedasticity. So we can say in simple that is a cross-sectional data, so it involves different kind of cars. Because of that, we said that the data may have a problem of heteroscedasticity. Now, if that's the case, if there is a problem of heteroscedasticity, so we already studied what are the consequences of having heteroscedasticity in our data. So we says that the coefficients are unbiased. So what does this mean? This means that if we have horsepower, so the coefficient it represents, that's the on average equal to this value beta 2, and similarly -127 on average equal to, this 0.39 refers to this HP, and then this -1.27 refers to SP, and then WT refers to this one. So on average these values are same, or it's still unbiased. However, the standard error are not efficient, or it is not the minimum values, or it's not best because of heteroscedasticity. So if that's the case, we cannot trust the t statistics value, and we cannot trust the f statistic value. So we says R square value, F statistics, and individual significance and signs of variables. We saw all these. We look into the interpretation. Because there is heteroscedasticity problem, so we cannot trust T values or F value. Now, here one question may arise that we haven't run any test. How we know that there is a problem of heteroscedasticity? Yes, that question should arise in your mind. We haven't checked yet. We are suspecting that there is a problem of heteroscedasticity, and because of that we are not going to trust the T or F values. So now we are going to check. We are suspecting, because it's a cross-sectional data, so by default we are suspecting that there will be a problem of heteroscedasticity. So if there is a problem of heteroscedasticity, we are not going to trust the value of the standard error or T statistic or F statistic. So now we are going to check if there is a problem of heteroscedasticity. So we are going first, before trusting our result, we are going to see that if there is a problem of heteroscedasticity and what could be done. So first we will check if there is a problem of heteroscedasticity through different tests. Once it get confirmed that there is a problem of heteroscedasticity, we have to fix it, and then only we will trust our result. If we check and that there is no problem of heteroscedasticity, then we can trust this result. So we are going to see that. So detection of heteroscedasticity through Eviews. So let me start now with detection. So now we are going to use our data and model we just estimated, and we are going to use Eviews and the test I just mentioned that how we're going to use each of these tests to check for heteroscedasticity. So we can, as I told you, there are a number of ways through which we can check the heteroscedasticity. The first one is graphical method, then the bridge pigeon or BP test, then the white test, and then some other kind of test. So now I'm going to do that one by one, and I'm going to tell you how we can use that. So first I will go to the graphical method. So the graphical method, the theory of this is straightforward. We said that this is the first and less standard way of checking the heteroscedasticity issue. So normally we don't use that, but still there is a way of looking into it. So we will just discuss it. Normally there are two ways of checking heteroscedasticity when you want to use the graphical approach. The first approach is you plot histogram of the square of the residual. So residual square, you take the plot of that. normally you wouldn't see a normal pattern of the residual, so that may be an indication of that there is a problem of heteroscedasticity. Or you can do the second approach is that you plot residual square against the predicted value of y, and if it displays some pattern, we say that there is a problem of heteroscedasticity. So in general, we would expect that the square of the residual is not correlated or having systematic relationship with the predicted value of the dependent variable. But if this is the case, we may suspect that there is a problem of heteroscedasticity. So let me show you that how it works on the next slide, then we're gonna demonstrate that on Eviews. So normally if you have the predicted value of y and you have the square of the error term, obviously this is the forecasted value as well. You don't get the original value of error, you get the forecasted value of the residual. So if it has a certain pattern like this, so that's an indication that it is a systematic pattern or an indication of a presence of a relation between these two variables. So we should suspect that there is a problem of heteroscedasticity if you get this kind of graph from plotting these two variables. Or you get a graph like this or this or this. So these are just possibilities of having different kind of, you can have much more graphical way of having these two variables. So all this will be indicating a systematic pattern and ultimately the presence of heteroscedasticity in your data. And then we will obtain, now we are going to obtain the histogram of the square residual from our data, the data we just obtained, and we are also going to plot the square residual against the predicted value of y, which I'm going to name mileage per gallon forecasted. So what I'm going to do, let me go back one slide. Sorry, so the two methods, the graphical approach, the histogram of residual square and the graph of residual square against the predicted value of y. So I'm going to do these two in Eviews, and I'm going to show you how we can see that there is a possibility of having heteroscedasticity in our data which we use. So let me show you first how you can do that in Eviews, and then I will demonstrate it. So in Eviews, steps to perform for squared residual histogram. First, we will go with the first approach, and we are going to see the residual histogram, the squared residual histogram. For that, first estimate the model that we just did it. Secondly, you have to save the residual of the above model. So the residual of the above model, you have to save that. How you can do that? You go to generate a new variable. You name it residual underscore square, so that the new variable you want to generate should be equal to residual underscore square. And then you can do that by object generate series, and then within that you write residual square. It should be equal to resid multiplied by resid, and then press OK. It should give you that residual square variable. What is resid? Resid is the default file for residual storage in Eviews. Whenever you run a model, the last model you run, its residual term will be there. Alternatively, you can generate the residual automatically from the result window as well. So I will show you that as well if I remember it by that time. Secondly, for you double click residual square. So once you have the residual square variable being generated, you open that variable by double clicking it. And once this variable is open, you go to the view window of that variable. You go to descriptive statistics, and then descriptive statistics and test. And then within that you select histogram and statistics, and it will give you an histogram. And then for this was for the first approach when you want to generate a square residual histogram. So obviously once you get the histogram, the computer will give you the histogram, then it's up to you to look into the numbers you get. Similarly, to apply the second approach, you have to graph the squared residual, we just created that variable and the predicted value of yi. So yi and the predicted value, yi here is mileage per gallon. So the predicted value of mileage per gallon and the square residual need to be plotted together. So again, I need to run the model for it, which we would run just once, and we can apply both approaches with running once the model. Secondly, I go to the proceed, then forecast, and for name forecast write mileage per gallon underscore forecasted, and I uncheck all other boxes. There are some other options there as well, so I will uncheck all that other boxes, and I will get a new variable with mileage per gallon forecasted, a new variable, and I already have residual square being generated. So I will open this new mileage per gallon forecasted and residual squared, both these variables open as a group, and then once I open them as a group, I will go to the view of that group, and I will select the graph, and within graph I will just select scatter plot and press OK. So it will give me the scatter plot of the two variable mileage per gallon forecasted and the residual square. And then I can see if there is a systematic pattern in that, and then based on that I can make a decision. So let me show you how we can do that in Eviews. So let me switch back to Eviews. So this is my model which I have run. We already saw how we can run this model. So once we have this model, first approach was to it's written here. So the first approach is I have to generate the histogram of the square of the residual. So for that I go to process so I will go here, object, generate series, and in generate series I write residual underscore square should be equal to resid into resid, and I press OK. So I got residual square variable. So that's one way of doing residual. Another way of residual is that in the results window, you go to proceed and make residual series, and you just have to name it residual 01, and then you generate a new variable multiplying resid with 01 with resid 01, and you can get again residual square. So that's another way of doing it. Okay, so that was generating residual square, and then I need the histogram of it. So I will open it, I go to view, then I go to descriptive and statistics, and then I go to histogram and statistics. When I click OK, I got the histogram of the residual. So you can see here it's by no way close to even normal. We will see that shortly. So and then I can freeze it, I can close this one, and then the second one was plotting residual square against the predicted value of mileage per gallon. So for that I need to generate predicted value of mileage. So again, run a model. It's already run. So I go to the object, proceed, and then forecast. When I click OK, here I have forecast name. So I will name it mileage per gallon, not F, and I will underscore forecasted, and I uncheck the other just not to get an extra values not required for this particular purpose. So I will click OK. This should give me a new variable mileage per gallon forecasted. So that's the forecasted value based on the regression model. So when I press OK, it gives me mileage forecasted. Now how we got that value? When you write equation, mileage per gallon is equal to 189.9597 minus 1.27 SP plus 0.39 HP minus 1.90 WT, and then you plug in the different value of SP, HP and WT, and you get number of values of MPG. So that's the forecasted value. So once I have the forecasted value, once I have the residual square, so I select these two, I open this as a group. So it asking me, should I close the group I early formatted? Yes, I don't need that, so I will just close it. So that's the new group now. This new group, now I want to make a graph of these two. So I will go here to view of the group, and then I go to graph, and then here I would select scattered. I don't touch any other thing, I just keep it to the basic, and I scatter plot between the two. Press OK. So I got a graph of these two variables. So now this is another graph which we were discussing, the graphical method. So let me switch to my presentation. Let's discuss it. So these are the results of the graphical method, and you can see that the histogram doesn't look good, not close to even a normality, and the mileage forecasted against the residual squared graph, well, although it doesn't show a very good systematic pattern, but up to some extent it gives some indication of having some relation, although it's not very clear. So in either case, a graphical method is not a very standard method, and we have ultimately apply a test. So I will switch back to the original slide. So we all were discussing that there are 4 ways of checking the heteroscedasticity. We check the graphical method. It is giving us some indication of heteroscedasticity, but we are not very sure. We want to apply some test. So let's now apply the BP test, and let's see how it works. So again, the theory of the test and then application through Eviews. So for applying BP test, first of all, we estimate OLS regression, and we obtain the square OLS residual from this regression. So we applied the test, we took their OLS residual, we already calculated the residual square as you have seen it for the graphical method as well. Secondly, we regress the squared residual on K regressors included in the model. So what we do, once we run the model, mileage per gallon regress on all explanatory variable, we took the squared residual. We remove the mileage per gallon, we use the squared residual as dependent variable, and we regress it on the other variables, the explanatory variables, which are K in number. So you can choose other regressors also that might have some bearing on the error variance. So we can think of adding some more variables as well, but or we can just stick to the variables which we used originally. So it's up to us, or up to the nature of the problem in hand. Then we have the null hypothesis. What is null hypothesis here? We said that the error variance is homoscedastic. That is, all the slope coefficient are simultaneously equal to 0. So we says that the model we run have no link with the other explanatory variable or the slope parameter. So if that's the case, we call it that there is homoscedasticity in our data. Let me write it. BP test is based on a simple logic. It says that first estimate the OLS regression, obtain the square of OLS estimators residual from this regression, and then use this residual square as dependent variable, use this squared residual as dependent variable, and regress it on K explanatory variables or regressor. So you had MPG being regress on number of variable, now once you estimate that, take the error term square and regress it on all explanatory variable again. And what does it do? You look for if this is statistically significant, or if this all coefficients, these coefficients associated with x1, x2, x3, if these are statistically significant overall, or f statistic of this is statistically significant. If that's the case, if it's not significant, so let me display it. So the null hypothesis is that the error variance is homoscedastic. And what does it mean? It means the slope coefficients are simultaneously equal to 0. So that's the case when this relation doesn't hold true, or your f from this model is statistically not significant. Against the other hypothesis in which we say in H1 would be that the slope coefficient are not equal to 0, or when f statistic is statistically significant, f is significant. So to put it in simple words, BP test is based on regressing the square of the residual on explanatory variable and checking the f statistic value of that regression model. If that f statistic regression is statistically significant, we say there is a problem of heteroscedasticity. If it is not statistically significant, we say there is no heteroscedasticity. So let me read the material I have, so that I explain this one as well, so that you get some clear idea. So as I said, first we estimate OLS regressor, we obtain its square OLS, we then use the square regress residual, and we regress it on the explanatory variable included in the model. Now here we can add more regressors as well, which are relevant, which we think that may influence the variance, but we can just stick to the variables which we use. It depends on the nature of the problem we have. So the null hypothesis is that there is no heteroscedasticity, or the data is homoscedastic. So when we have this null hypothesis, it means the regression we are estimating by regressing error square on the explanatory variable having 0 coefficients. And then alternative hypothesis is that we have a problem of heteroscedasticity, or the coefficients are not equal to 0, and or the error variance is heteroscedastic. So we use f statistic from this regressor with k minus 1 and n minus k degree of freedom. So k refers to the number of explanatory variable in the model and refers to the number of observations. So these are the 2 degrees of freedom. You shouldn't be worried about these too much, because at the end Eviews do automatically provide this thing. You don't have to do it manually. So if the computed f statistic is statistically significant, then we say there is a problem of heteroscedasticity, and we reject the null hypothesis of homoscedasticity. Now, it may sound very complicated when you look at this slide, and perhaps the way I explain it, it may sound complicated. However, it's not that complicated when you come to the application of it. So in Eviews, when you want to apply this test, it's a very simple procedure, although it may be in a few steps, but it's a very simple procedure. I will show you in a minute. So first of all, you have to estimate your regression model. You estimate the same model which we did it, and then what you do, you go to the output window of the regression model, you click on view. In view, you select residual diagnostics. Within that, you select heteroscedasticity test, and then a box pop up. In that box, you select this BPG test, and with all default option, and you press OK, and you get the results. So let me demonstrate that how we can do that in Eviews. So this was the results of the model when we run the econometric model, the same model. So I go here to view, then I go to the residual diagnostic. So it's the third last. Then I go to the heteroscedasticity test. So this is the options you should select. Once you click OK, this window pop up. So now you can see here, it is by default the first one is BP test. Now look at here. What does it say? Dependent variable residual power 2. So residual square is the dependent variable and regressor are constant, SP the speed, horsepower and weight. The three explanatory variables and the constant are same and the residual square of the model is being regressed. So when I press OK, it gives me the results of the BP test in simple word. So what does it gives me? It gives me the F statistics, which I have to calculate its degree of freedom, which I just told you about a while ago. And this is the results of the regression. Here the residual is residual square and it's regressed on the three explanatory variables. Its R square value, its F statistic value. Look at this value, F statistics 11.78700 and the probability value. So it's statistically significant. So what does it says? We says that our null hypothesis is, let me remind you, refresh your memories. The null hypothesis is that there is no heteroscedasticity, or the variance is homoscedastic, or these coefficients are equal to 0. So that's the null hypothesis. And the alternative hypothesis is that this data is heteroscedastic, the variance is heteroscedastic, these coefficients are not equal to 0. So now look at the F statistic value. What does it say? It says on collectively or in overall, these coefficients are not equal to 0, or in other words, the error square term is linked with these variables, or in other term, the variance of this error term is not equal to 0 or not homoscedastic, so it's heteroscedastic. If I freeze this output, we can do this variable this test manually as well. If I freeze this, I keep this here, I close this, and keep in mind that residual square was regress on this, so I can do that manually as well. Residual square regress on constant, then SP, the other one is HP, so I take HP and then WT. So if I open it as a equation, I take C at the start just to take it in a standard format. Look at it. Do you see any difference? It's the same regression, 659, 659, minus 640, minus 640. So you can do it in the other way as well. The only difference is that here the degree of freedom here is with 377. Otherwise, their F statistic value is also the same. So that gives you the idea that the only difference in the two is that here the degree of freedom here is taken as per the normal regression, and here it's as per the way the test is defined, that you take n minus k and n minus 1 degree of freedom. So so that's the only difference. That's why you get here the probability value of very highly significant is slightly different, but at the end of the day both are statistically significant at 1%. So I will just close this one, and I will bring back again, repeating. You go to view, you go to residual diagnostic, you go to heteroscedasticity test, you select BP, the first one, you press OK, and this is the result of the test. So that was the case of the heteroscedasticity for BP test. And let me switch to the output. So when I press OK, I got this result. I show you on the Eviews as well how you can get this result, and it's very clear that F statistics with 3 degree and 77 degree of freedom strongly reject the null hypothesis, which says that these coefficients are overall equal to 0, or the variance is homoscedastic, or the residual have no influence of these variables. So that's strongly rejected, and we said that there is a problem of heteroscedasticity. So BP test confirmed that. Now going back, the third test is white test. So now we're gonna see what is white test and how it works. So white test, the theory part, again Again, if you look into it, this test is also based on the square residual, and we regress square residual on the regressor and the square term of these regressor and the pairwise cross product terms of the regressor. So now again residuals are regressed, but this time using the variables in an original form, then taking its squares and then taking its pairwise combination, and the rest of the procedure is very much same. We obtain r square value from this regressor and multiply it by the number of observations. So we calculate n r square, and then under the null hypothesis that there is homoscedasticity, this product follow the chi-square distribution with degree of freedom equal to the number of coefficient estimated. So we then believe that nr square follow the chi-square distribution. Now contrast it with the BP test that's based on F statistic. This test is based on chi-square distribution, and here the degree of freedom is equal to the number of coefficient estimated, and the null hypothesis again is same that the coefficients are collectively equal to 0, or it's homoscedastic against the non-homoscedastic. It should be noted that the white test is more general and more flexible than the BP test, and you use it for a larger samples as well. So let me tell you how we can do it in Eviews. It's the same procedure. It's the same procedure for heteroscedasticity white test as well. You have to select the white test instead of the BP test in the window which we just tried for BP test, and when you press OK, you get these results. So let me show you how we do it in Eviews, and then we can see here. So view this residual diagnostic test, heteroscedasticity test, and then here you have this white test, and here it says residual square being regressed on the square residual on the cross product of the original regressor and a constant. So when I press OK, so here you got, if you look at the regressor, residual square regress on SP square, SP and HP, so that's one interaction term. SP, so it's a pairwise, SP, WT, then SP itself, SP square, SP interacted with HP with WT. Similarly, HP square, HP WT, and HP WT square and WT. So that's this is chi-square observation multiplied with r square 17.28, so nr square, and it's also with 9 degree of freedom. It's also statistically significant. So this is the output of white test. We can see here that residual square being regressed on constant, then the variable SP, its interaction with WT with HP and the square of it, then the variable HP, its interaction with WT, and SP WT was already here, and then the variable HP square, then WT variable and WT square, because the HPWT or WTHP is same thing and SPWT or WTHP is same thing. So this is the residual square being regressed on the variable itself, their square term, SP square, HP square and WT square, and their pairwise interaction term. And we says that observation multiplied by r square of this regression follows a chi-square. So we take the r square value of it, which is 0.213395, and we multiply it with number of observation. Let me take my calculator. So this is 0.21333 and whatever the value is. So I paste it here somewhere. I don't know how to paste it, so let me write it down. So this is my calculator. So I take the value 0.21335 and multiply it with number of observation, sample 1 to 81, so number of observation 81, so I multiply it with 81. So I got 17.284. This is the same value, observation to r square 17.28498, and we says that it follows the chi-square distribution. So it's chi-square distribution, and then we see that degree of freedom. So degree of freedom was equal to the number of parameter minus 1. So 1, 2, 3, 4, 5, 6, 7, 8, 9 and 10 constant is included, so it become 10. So you minus 1, so that make it 9. So this is the value of chi-square. This is the probability for chi-square. So it's statistically significant at 5%. So it indicates that there is a problem of heteroscedasticity in this data. We reject H0, which says this all parameters are equal to 0, against that these all parameters are not equal to 0, and it's an indication of heteroscedasticity. So in white test, the following step needs to be followed. First, we regress the model on all the explanatory variable. Then we can go to the output window of that regression model. We select residual diagnostics the same way we did it for the BP test. Then we select heteroscedasticity test, and then we select white with all default options. When we press OK, the results we get, these are the results which we got. And as I told you during the estimation process, that the observation into the R square which is equal to 17.28, that's n R square, that follows the chi-square distribution with n minus k minus 1 degree of freedom, and that's statistically significant at 4.4%. So we can conclude that we are going to reject the null hypothesis, which says that there is the variance is homoscedastic in favor of there is no homoscedastic, or the other way. In short, we can conclude that our data has a problem of heteroscedasticity. So this was a white test. Now going back to the main slide. So we got graphical method, we got BP test, we got white test, and then finally we have some other kind of test as well. Instead of doing it one by one, I will just straight away take you to the other test and show you how we can do that. So for other test, in principle, as I told you, we only need one single test to confirm the presence or absence of heteroscedasticity in our data. However, we have several tests which we just applied, two of them, BP or white test, and then there are some more tests as well, such as Harvic test, Glacier test, ARC test. These are the three tests which are provided in Eviews. So we can apply these tests as well. So very quickly, for Glacier test, once you go to the view and then you go to the error diagnostic test, then you select the Harvic test, and here you can see that instead of regressing residual square, it regress log of residual square on the explanatory variables. The rest of the story is same. Similarly, in Glacier test, absolute residual are regressed on the explanatory variable. In ARC test, the residual square is regressed on the the square residual on the legged square residual and a constant. So you can select the number of legs as well. I will show you with the output. So these are the outputs, respective outputs of all the three methods. These are pretty straightforward, the first two ones. The third one is when you regress residual square on the residual and its lag value. I introduced the lag variable earlier, that when you measure the variable in period t and its lag value would be the variable in period t minus 1. And then you can think of the second leg in you can add one more residual square minus 2 with taking the second leg, the third leg and the fourth leg. So while applying this method, you can select the number of legs. And the problem with this method, which I can see here, is that if you increase the leg or if you change the leg, the result would change, and it would obviously affect the analysis. To conclude this session and the testing process and the detection of this heteroscedasticity, my simple suggestion would be to you people, while applying detection of heteroscedasticity, would be to stick to one particular test. Use that test and that's enough. Don't go for 5 or 6 tests for checking one thing. So what I would suggest you that for you for this particular course, I would advise you that when you have to check heteroscedasticity, first go with the graphical analysis, so that will give you some hint, and then pick BP test if you have a small data. If you have large data, then go for a wide test and stick to these two only. Don't go for the other test. With that, I will conclude my session. I hope you like my session. Feel free to ask questions in comment or through emails, or you can suggest me the topic which you don't understand. I can make a separate video on that as well. Feel free to write me, subscribe the channel, and I hope we will have some more good videos in future. Thank you.